Okay.
Andrea, are you ready?
Yes.
Yeah, okay, I'll introduce you here. So it's my pleasure to welcome Andrea Solotar. She'll talk today about on the tau tilting Hochschild cohomology of an algebra.
Okay. Thank you very much. Thank you for the invitation and sorry for the problems with the apps. I hope this will work. Okay, so I will write a bit less than I expected, but well, let's do it. So the idea is that I want to talk about Hochschild homology and cohomology and a new theory that I have defined. This is the last part is a joint work with, let me try to write it, with, okay, it is not working. So with, oh, sorry. Oh, so what happens here? I'm sorry. I don't know why it is not writing. Give me one moment. I tried it before and it worked, but okay.
Oh, now you cannot write on the screen?
Now I cannot write, yes, I don't know why.
Oh,
because I'm not in the app, yeah.
Ah.
I'm trying to do it and it's not working.
Okay.
Sorry. Okay, let me, I don't know what happens with this. Okay. Oh. Let me start again.
No, direi che c'è 5 minuti di prova.
Yeah, it is not responding anymore. Okay. So it's not working. Let me try again.
Yeah, try to share your screen again.
Yeah. No, I try with this one. It is not working.
Sì, perché c'è 5 minuti di prova, però sono una parte.
Okay. Will you please give me 5 minutes and I will try to do it
Oh, yeah, sure.
differently. Okay, so I will disconnect and then connect. Yes.
Yeah, sure.
Sorry for this.
Yeah, no worries. Are you working? Oh, there is a way that I can do that.
Play through the speaker.
Yeah. I mean, I can.
We just won't be able to talk.
Okay.
But I think it's more important that we hear her for the most part.
So can you disconnect from audio before I do this?
Should I leave and then
Is there a way to just disconnect?
disconnect? Oh, yeah, there should be. But the thing is, I mean, the main thing is, they want me to connect it. So the voice here is kind of speaker. No.
No, are you sure you can do that though? I don't think you can play
I mean,
sound through that.
Yeah, I was doing with the class.
Oh, okay.
Yeah,
All right.
I'm not sure. Just try. What do I try? Oh, my it's still like I used to every time that it's do you know where is checking microphone?
Does it have to be like
Then anyway, that I check microphone and speaker. You know what? Check settings. I guess settings. Yeah, that is. Maybe settings. Maybe you can't do it. Yeah. I was just. I want to make sure that I can hear something. Someone talks. Are you connected to your phone?
Yeah, but everything's disconnected. Like
Try to connect it.
sound and video are disconnected.
Okay, just can you connect the sound? If you sound, yeah, connect to the sound. So and then say something. So yeah, just want to make sure we can hear.
Testing. Can anyone hear me? Can anyone?
Unmuted. I can hear it from your tablet. Maybe it's like for audio like for audio preferences are set to HDMI. So that would be on this has to be on HDMI.
Are set to HDMI. Okay. Do you have connector with you? HDMI connector. If you have, okay. Now try again.
Testing.
I think it's a setting on your iPad.
Not probably.
You have like audio settings. HDMI.
Sound.
System sound. Maybe it's not gonna. It's not gonna.
Okay, so I tried with with the whiteboard, with some whiteboard, and it works. But now let me try with you.
Yeah.
So just a moment. Let's see if it works. If this time it works. So I'm showing the meeting. But it was not the screen, it was just the whiteboard. So just a moment, please.
Okay.
I don't know how to get the sound.
Yeah, this is, I guess, okay. Audio. Just
Okay, again, sorry.
yeah, let's see.
Oh. Yeah.
So should we connect to this for the speaker or this for the microphone?
Maybe after talk start.
No, I don't know how to use this microphone.
No, not. That's what.
Okay. And now let me share.
Yeah, go ahead.
Wait.
Yeah,
So we're using.
so
Yeah.
let me, now it's writing at least.
Oh, yeah.
Okay, okay, so let's try to do it like this. I'm sorry for all the inconvenience. Okay, so as I said, I am trying to work and to talk about some recent work with Claude Cibils. Then Marcelo Lanzilotta. Okay, now I know what happens. Yeah. Sorry for my calligraphy, and Eduardo Marcos. Okay, and this theory is called the tau tilting, the tau Hochschild homology and cohomology. Okay, so the thing is that usually, well, it is well known that Hochschild homology and cohomology of an algebra, they are invariants that are related to what is called the smoothness of the algebra A, the algebra we are considering. So this is Hochschild homology of A and Hochschild cohomology of A. They are related to the smoothness of the algebra A. This is just an introduction. I will give definitions in a few minutes. Okay. So what is classically what I mean by this is that if the global dimension, or more or less that the global dimension of A is finite, if and only if the Hochschild homology and the Hochschild cohomology of A are zero for all I big enough. Of course, this is not true like this, okay? So this is not going to be true. So we want to prove some statement like this, at least in some situations, okay? So there is a classical setting for this, that is when A is a commutative algebra. And I will start describing what happens in the case of a commutative algebra, and then what happens in the case of, in the general case of a non-necessarily commutative algebra of finite dimension, which is finite dimensional, okay? So I will start with the details. Sorry for this line that I don't want to erase now. Okay, so the first thing is the commutative case. Okay. So in the commutative case, I am going to consider, as always, K a field during all the talk. And A in the commutative case is going to be an algebra which will be essentially of finite type. So what is an algebra essentially of finite type in the commutative setting? In the commutative setting, it is an algebra A, which is a quotient of a polynomial algebra in some number of variables divided by an ideal spanned by some number of polynomials, okay? Either this or a convenient localization of this. So without the localization, it's just of finite type. With the localization, is essentially of finite type, okay? Okay, there is, in this case, a notion of smoothness. So to say that A is smooth is the same as saying that, I'm trying to define smooth, that A is geometrically regular, okay? And what is to be geometrically regular? Well, this is a local definition. It is if and only if for all maximal ideal M of A, consider the algebra A localized in M, that means in the complement of M. So you have in this local algebra a maximal ideal, which is just M. It is the only ideal that is left, the biggest ideal that is left. So one can consider this localized algebra divided by the maximal ideal. It is going to be a field, and we consider the dimension over this field of the ideal divided by the square, which is a vector space over the field. And it has to be equal to what is called the embedding dimension of A, M. Okay, so what do I mean by this? Well, let me give you an example. Suppose that I am in dimension 2, a fine case, and I have a curve like this. So here, it is a curve, so the embedding dimension is going to be 1. And if we look at what happens at each point, there is the tangent space at each point is equal, it has dimension 1, okay? Like this, or here it's like this, etc. Okay, well. But if we look, for example, at a curve like, I don't know, this one, okay? The problem is that in this point, even if the embedding dimension is equal to 1 because it's a curve, at this point we have 2 that the tangent space has dimension 2. So this first curve is geometrically regular, and this one, or smooth, and this one is not geometrically regular or smooth. Okay, so this is the main idea. I'm just trying not to give the precise definition, but just an idea. Okay, and there is a theorem that one can mention a theorem by either by Serre or by Auslander and Bushman, saying that A is smooth for A commutative if and only if the global dimension of A is finite. Okay, so this result is the key to the definition of a smoothness, an algebra being smooth in the non-commutative case. Okay, so in the non-commutative case, we are going to say that an algebra is smooth if and only if it has finite global dimension. Okay, so what happens is that there is a very famous theorem, which is the theorem by Hochschild, Constant, and Rosenberg from 1961, that says that if K is a perfect field, then the Hochschild homology in degree n of A also, but this is if A is smooth, this is also an hypothesis, the Hochschild homology in degree n of A is isomorphic to the exterior power and power over A of an A module, which is called the module of scalar differentials. In other words, this module of scalar differentials is an A module that is going to be spanned if an algebra is a quotient of a polynomial algebra in n variables by dx1 differentials to dxn, one for each variable, divided by some relations. Okay? So, for example, suppose that A is equal to k of x1, x2, divided by the ideal spanned by x1 squared minus x2 to the power 3, let's say. So in this case, omega 1 is going to be spanned by dx1 and dx2 under the relation that 2 times x1 dx1 minus 3 times x2 squared dx2 has to be 0. Okay? So the fact is that if A is smooth, one can prove this theorem, for example, in characteristic 0, and then, well, this is not the same n. Let me put an R here, okay? Then HHR, the Hochschild homology of A in degree R, is going to be 0 for all R that is bigger than the global dimension of A. Okay? So this is one side of the result. Later on, at the beginning of the 90s, there have been two results, one by the Buenos Aires cyclic homology groups, and the similar result by Abramov and Michelin Viguet. The only difference is that this one is only for characteristic 0, and this one is for arbitrary characteristic, saying that if A is not smooth, then for all n, for all R positive, there exists an I that is bigger than R, such that the Hochschild homology of A in degree I is different from 0. Okay, so putting both things together, we get that A in this commutative case is smooth if and only if the Hochschild homology of A is 0 for I big enough. Okay? But this is only the commutative case. Okay? And what happens with cohomology? Well, later, Abramov, together with Iyengar, proved a similar result for cohomology. So the consequence is that in the commutative case, smoothness is completely characterized by the annihilation of either Hochschild homology in big enough degrees or by Hochschild, the annihilation of Hochschild cohomology. Okay, so if there is any question, please interrupt me. Yeah. So let me now go to the non-commutative case, or non-necessary commutative case. Okay. So independently of all that I have been telling up to now, the thing is that in the non-commutative setting, the problem has been studied for a finite dimensional. K-algebra. Okay. One reason for this is that, well, when A is a commutative algebra, there is a model coming from algebraic topology that helps to helps to compute the Hochschild homology and cohomology of the algebra. In the non-commutative case, well, this is no longer true. And so we need something else. And so we consider A, which is finite dimensional, because in this case, there is a theorem by Pierre Gabriel saying that if we have a finite dimensional k-algebra, there exists a quiver Q and an admissible ideal I, such that A is Morita equivalent to the quotient of the path algebra of the quiver divided by the by this ideal. Okay, and it can be proved that the quiver is unique. This quiver is unique, but the ideal is not necessarily unique. Okay, and there are very simple results. So in this setting, very simple examples. In this setting, Happel proved that if the global dimension of A is finite, then the Hochschild homology of A with coefficients in A is 0 for I big enough. Okay? We can say, well, this is easy, but the thing is that when we are talking about the global dimension of A, we are talking about, well, projective dimensions of A modules. But when we are talking about the Hochschild homology, we are looking at A as an A bimodule. We are looking at bimodules and not, we are not looking at modules, okay? So the problem is going from modules to bimodules. Well, Happel proved that this is true, okay? Okay, so in the same paper, I think it's more or less in the 1990 or 1989, there is a question that was later known as Happel's question. That is the converse true? Meaning, if we know that the Hochschild cohomology stops, of the algebra stops at some degree, then can we be sure that the global dimension is finite? Okay, so this has been studied for several years, and at some moment, I think it was 2004 or 2005, there was a counterexample. The counterexample is a very easy algebra. It's a local algebra, meaning that the quiver has only one vertex. So you have one vertex, and you have two loops, X and Y, we call them. And the algebra is the quotient of the non-commutative algebra on X and Y divided by the ideal spanned by the square of X, the square of Y, and a kind of commutation relation, which is Yx minus Qxy, where Q is not a root of unity, okay, for all n. Okay, so what happened with this algebra is that the global dimension of A is infinite, for a very simple reason, that it is the following one. The reason is that we have either this x squared or this y squared here. And so we have a map from the algebra k of x divided by x squared, which is an algebra, a commutative algebra of infinite global dimension. And then it embeds in A. And then we have a map P going again to Kx, a morphism of algebras, divided by x squared. That sends, of course, x to the class of x and y to 0. Okay? And the composition is the identity of Kx divided by x squared, which makes that Kx divided by x squared is a direct summand, and then since it has infinite global dimension, A is also going to have infinite global dimension. Okay, so it's infinite global dimension, and in a paper by Buchweitz, Green, Madsen, and Solberg, they computed the Hochschild cohomology, and it happens that the Hochschild cohomology of A in degree 0 has dimension 2, the same for the Hochschild cohomology in degree 1, the Hochschild cohomology in degree 2 of A has dimension 1, and moreover, the Hochschild cohomology of A is 0 for all I greater or equal to 3. Okay? So here we have an example of an algebra which is non-commutative, finite dimensional. The Hochschild cohomology stops quite in a very, very quite small degree. So the last one non-zero is in degree 2, but the global dimension is infinite. Okay, so the answer to Happel's question was no. Okay, so we have that even over a field of characteristics 0, the finiteness of the global dimension is not in principle related to the finiteness of the Hochschild cohomology. In 2007, there was a paper by Yang Han where he proved that the Hochschild homology of this same algebra A, the counterexample to Happel's question, is infinite. Okay, so it is non-zero in infinitely many degrees. Okay, in this way, he showed that, at least for this example, the Hochschild homology is more adapted to the global dimension being, to describing if the global dimension of the algebra is finite or not, than the Hochschild cohomology. And so, in this same paper, he established a conjecture that is known as Hans conjecture, saying that if the global dimension of the algebra is not finite, then the Hochschild homology of A is non-zero in infinitely many degrees. Okay? And in the same paper, he proved it. He proved the conjecture for monomial finite dimensional algebras. Okay? Monomial means that the ideal, if you write your algebra A like KQ over I, this ideal I can be generated by monomials. Okay, so up to date, Hans' conjecture has been proved for several families of algebras, but it is still open. Okay, so it has been proved for monomial algebras by Hans himself. It has been proved for Kosul algebras. Also for generally graded algebras, but only in characteristic 0. And also for other families, some more families that I will not mention here of algebras, but it is, the general case is still open, okay? But today, I want to talk more about cohomology than about homology, okay? Okay. So. Okay. So the problem is that, also let me mention complete intersections. So complete intersections, algebras of type K of some variables X and some variables Y, they are generalizations of this divided by some power and then a commutator, commutation. Okay, so this is the state, the conjecture. So we define with Claude and Marcelo and Eduardo another theory that is called tau Hochschild cohomology. And we have proved, I will going to talk to you about this, that is more adapted to describing the finiteness or not of the global dimension of an algebra than the Hochschild cohomology itself, that, as we have seen, is not adapted to this. Okay? Okay, so now for this I have to mention some definitions. Now I will have that A is a k-algebra, finite dimensional, and M and N are left A-modules. Okay, and we have a functor that we will consider, which is the dual functor, which is just the dual with respect to K. And we have the transpose functor, transpose, which is defined by Auslander-Reiten. It is defined in terms of the minimal presentation of the algebra, and then one takes duals, and then one takes the co-kernel of the map, but I will not give the precise definition, because I'm interested in another functor, which is called tau, and it has the name of the Auslander-Reiten translation, which is the dual of the transposed. Okay, it is the composition of both functors. Okay, and the thing is that it is very useful, mainly because of a formula that is called Auslander-Reiten duality formula. Which established that if you want to compute the x1 over A of M with N, it is isomorphic, naturally isomorphic to the dual of computing the ohm of A modules between N and the Auslander-Reiten translate of M. But we have it to take a quotient, so there is a bar here. So this bar means that we are taking the quotient by the idea spanned by the maps that factor through injective modes. So the thing is that if, for example, N is injective, then this is going to be 0, which is obviously true if we look at the left-hand side. Okay. So one of the main ideas of tau tilting theory is that it is interesting to replace this time, each time, this quotient appears by A n tau of m. So in this way, we recover the morphisms that factor through injectives. Okay? So this is the philosophy we are going to follow here. Okay. So now let's go back for a moment to Hochschild cohomology. So now we are going to take lambda, an algebra, and X, a lambda bimodule. Now I am going to consider the Auslander right and translate with respect not to the algebra lambda, but to the enveloping algebra of lambda, okay? And I'm going to consider the Hochschild cohomology in degree n, for n greater or equal to 1, of lambda with coefficients in X, okay? By definition, this is the X n over lambda e of lambda with coefficients in X, and it is known that this is the same as the x1 over lambda e of, this is Heller's functor, CCG functor, n minus 1 of X, of lambda, this is lambda here, with coefficients in X, okay? The Auslander-Reiten duality formula, so this is the Auslander-Reiten duality, says, because it's only for degree 1, that this is the dual of the hom lambda e, okay, of X with coefficients in the Auslander-Reiten translate here of omega n minus 1 of lambda, and here we have to take modulo morphism factor that factor through injectives, okay? So following this idea of tau tilting theory, with the coefficients in X as the dual of the hom lambda e over lambda e of X with coefficients in the Auslander-Reiten translate of the omega n minus 1 of lambda here without the bar, so without quotient by these morphisms, okay? So this is our definition. There is also a definition of tau here, Hochschild homology of lambda with coefficients. We think about it in the same way, and it turns out to be the hom lambda e of the dual of X with coefficients in the tau of omega n minus 1 of lambda. Okay, so the dual changed type here, okay? But today, I am not going to talk about this one. I am just going to talk about this. Okay, perfect. So, these theories, Hochschild cohomology, the tau Hochschild cohomology, satisfies that it is a Morita invariant, but not derived invariant. Because in fact, we show an example showing that it is not a tilting invariant. Okay, and in order to compute it, we need a minimal resolution of the algebra, okay? So how to compute it? Okay. So how to compute it? So now consider the minimal projective resolution, a minimal projective resolution of the lambda bimodule lambda itself, okay, like we do when we want to compute Hochschild cohomology. The thing is here we have a minimal resolution, a minimal projective resolution, because it's a finite dimensional algebra. So we have this minimal resolution, lambda, okay? And in this resolution, we have morphisms that we call D0, D1, Dn, etc. And then if we want to compute, for example, the Hochschild homology with tensor over lambda e with a bimodule, if we want to compute Hochschild cohomology with coefficients in a bimodule, we apply a factor ohm, and we have to compute the homology of the following complex. Then this one, etc. etc. And then we are going to call this map now. This is delta 1, this is delta 2, and this is going to be delta 3, etc. Okay. And the thing is that we have proved that for all n greater or equal to 1, we have that the Hochschild, the tau Hochschild homology of lambda with coefficients in X is the co-kernel of the map delta n, okay? And similarly, I have not considered the complex that we use to compute the Hochschild homology, that is just tensoring, but in that complex, the maps are going to be called delta n prime, and in degree n, we are going to compute just the kernel delta n prime. So the difference with Hochschild cohomology is that for Hochschild cohomology, at each step, we consider the kernel of delta n divided by the image of delta n minus 1. But here, instead of considering kernel divided by the image, we consider at, for example, here, all the space divided, we just consider the co-kernel of this map, okay? So we get more elements here. So in general, as a corollary, we are going to have that for all n greater or equal to 1, there is an epimorphism from the Hochschild homology, from the tau Hochschild homology to the usual one. And there exists a monomorphism from Hochschild cohomology to the tau version of this Hochschild cohomology. Okay? So in general, this tau homology and this tau cohomology, they are bigger than the usual, than the classic versions. Okay? So what we have proved, okay, another result that says that if the global dimension of lambda is d, but this is very easy, no? Then the Hochschild cohomology, the tau Hochschild cohomology of lambda with coefficients in itself is 0, as well as the Hochschild homology of tau Hochschild homology of lambda with coefficients in itself for all n that is bigger than the global dimension. This is because we are working with the minimal resolution, and the minimal resolution stops, okay? So we get, if the global dimension is finite, then the Hochschild, the tau Hochschild cohomology and homology stop. Is the reciprocal statement true? Well, up to now, we have just a partial answer to this, but it is quite satisfactory for the moment. And let me just mention one statement that I am going to generalize in a few moments, that if I have a finite dimensional or lambda, let's say finite dimensional algebra, local, which is local, that means that the quiver has just one vertex, then we have that the global dimension of A of lambda is finite if and only if the tau Hochschild homology of lambda with coefficients in itself is 0 for n big enough. Okay? And the idea to prove this is that we first verified, and this gave us the idea that for the algebra that is the counterexample to Happel question, this one that I have already mentioned, with Q not a root of unit, the Hochschild cohomology, the tau Hochschild cohomology of lambda, this is lambda in this case, is different from 0 for all n. Okay? So in this way, we say, well, this theory is more adapted to describing smoothness than usual Hochschild cohomology. Okay? In fact, we have a more general version of this statement. So we are going to suppose now that A, let me call it A now, KQ over I, a finite dimensional algebra. We are going to say that A is of infinite, and this is a definition, infinite plus global dimension. It's a bit more than infinite global dimension. If and only if there exists a pair of vertices in the quiver such that in A we have a non-zero path from X, this is the source of the path, and this is the terminus of the path from X to Y, a non-zero one, such that if we consider the Tor A of the simple model, right a model on Y and left a model on X, okay? Why this Tors? Because this gives the projectives appearing in the minimal resolution, okay? So we are supposing that there is a non-zero path from X to Y, and this Tor is infinite, okay? So it is different from 0 in infinitely many degrees, okay? So this is a new definition about infinite plus global dimension. So some remarks here is that infinite plus global dimension implies infinite global dimensions a bit more. Because in this case, since these objects appear in the minimal resolution, the minimal resolution will never be 0, okay? And a second remark is that we have infinite global dimension and the algebra is local, then of course there is only one vertex, and this implies infinite plus global dimension. Okay? So our theorem is that if we have a finite dimensional algebra written like this, and it has infinite plus global dimension, then the tau Hochschild homology of A is going to be different from 0 for infinitely many degrees, for infinitely many values of n. Okay? You can say, well, here you have this hypothesis of being infinite plus global dimension, but the remark is that we don't know of an example of algebra such that A is of infinite global dimension and not of infinite plus global dimension. Okay? And we think that both notions coincide, but we have not been able to prove it yet. Okay? So the idea is that at the end, we get this theory that is, as I said, more adapted to describe the finiteness or not of the global dimension of A. And we also have a homology theory, okay, the tau Hochschild homology of A, that we plan to use to study a, let's say, tau tilted version of Hans' conjecture. Okay, so this is what I wanted to tell you. I'm sorry for the technical problems, and I hope that anyway it has been possible to understand something. Thank you.
Can you hear us, Andrea?
Yes.
Yes. Sorry, can you say something again? Can
Sorry?
you hear me?
Yes, yes.
Oh, okay. Okay, any questions for the speaker? Okay, Tekken has one here.
Yes.
So Andrea, actually I have a couple of questions. Oh,
Yes, tell me.
okay. The first one is about the literature. So if you scroll up a bit with the Happel's proof, it was kind of at the beginning. I mean,
You
maybe
mean,
yeah, just it's related to,
Yeah.
let's see.
Maybe here. Okay, here.
Yeah.
Okay.
So wasn't there a theorem before that you show, like by Sarah, if A is smooth, then it is if and only if global dimension is kind of less than infinity? And also one other theorem is A is smooth. If A is smooth, then Hochschild homology is 0 for I bigger than 0. So isn't this Happel's proof is kind of like just combining that too?
Okay, so please let me mention that there is something that you mentioned that I've forgotten is that as you said, for finite dimensional algebras, it has been proved by Keller that if Hochschild, if the global dimension of the algebra is finite, then Hochschild homology is 0 in all positive degrees. Okay,
all
not
positive
only
ones.
all
Okay.
positive degrees. That this is by Keller and it's mentioned in Hans' paper in 2007.
Oh,
Okay.
I see. Okay.
And you mean that Sarah proved? Can you say it again, please?
Oh yeah, that's Sarah's proof before. Like if A is smooth, then global dimension is less than infinity. That's kind of if and only if statement. And I guess like if you combine that too, that gives kind of Happel's proof, if I'm not mistaken.
But I don't think that Sarah, you mean for a non-commutative setting?
Oh no, yeah, it was commutative setting, I guess.
No, but if the global dimension is finite, then Hochschild homology stops. This is very, very old because it's Hochschild, Constant Rosenberg is from 61.
Oh,
Okay.
I see. Okay.
Yeah, but Happel's proof here is not it's different from this, because in fact what he proves is that if you're working with a finite dimensional algebra, then if the global dimension is finite, then the global dimension, if I'm right, of A tensor A op is of the enveloping algebra is also going to be finite, and this is why this projective dimension of A as an A-bimodule it's finite, so Hochschild cohomology stops. Yes.
I see. Okay, yeah, that's clear now. And one other question, like there is an embedding from Hochschild cohomology to like tilting of Hochschild cohomology, right?
This tau Hochschild homology.
Yeah, tau
There is an embedding in one case. I will go to this.
Yeah, I guess like on homology it is one way, and on cohomology
here it is. It is an epimorphism for homology and an embedding for cohomology. Yeah.
And I am assuming there is also we can define also a bracket for the tau cohomology, right?
No, this is a problem. No, we cannot.
Oh,
Because,
I see.
And we have been trying for a long time to do so, even for H1. Okay, so suppose that you want to define it here, and of course, suppose that you want to take x equal to lambda. Okay, so let me go back to the definition. Well, the first problem is that you have the only possible way is to use minimal resolution, but this may not be a problem because we know that we can change resolution. But the problem is that we have to work with this co-kernel, okay? And even if we are no longer talking about derivations, we are talking about maps that are derivations are inside. But there are more things that are not derivations. There are lambda with coefficients in lambda. So when you try to do the bracket, because the bracket should be the usual bracket, okay, sometimes you cannot do the compositions.
I see.
Okay, and this is really a pity. This is a problem of the theory.
I see. Okay, so then we cannot even clearly define the bracket there. Okay, I see. And I mean, you tried something, so maybe I can like even we can define like. Do you think that embedding will carry the bracket?
Yes, but you cannot define a bracket, for example, between things that are outside the H1
of the derivations. Yeah, I see.
That are not derivations. And this is a very important problem, but so one thing I should mention that I have not said is that this theory is not a derived functor, because it if it was a derived functor, you would be able to change resolutions. But here you really need to work with the minimal projective resolution. And the
I
problem
see.
is that you need to work with this minimal projective resolution because even for the definition of the Auslander rate translate, you need a minimal resolution. Okay.
I see.
So from one side, you don't send to zero the maps that factor through injective, which is good. But on the other side, you lose the freedom of changing resolutions.
I see. Okay.
Okay.
Yeah, I mean that makes sense. Yeah, there are way more stuff than the derivations on the right side. Okay.
Yeah, exactly.
see.
And
Okay.
we have examples where it is really bigger. I mean, there is an embedding and it is a proper embedding in some cases.
I see.
Yeah.
I see. Thank you.
Yeah, thank you.
Other questions for the speaker? If not, let's thank Andrea again for a nice talk. Yeah.
Okay. Thank you very much.
Yeah, thanks. I really enjoyed that. So.
Okay, and again,